Hello, everyone. Good afternoon. A warm welcome to all of you who decided to join this webinar and hear about an introduction to Urban Atlas. Urban Atlas is a part of the portfolio of the Copernicus Land Monitoring Service that we call CLMS for short. And today we hope to raise your attention to these products, and hopefully you will find some interesting data for your analysis. My name is Ana Souza, and I'm responsible for the current Urban Atlas production at the European Environment Agency. The agency has been entrusted, as I suppose many of you know already, we have been entrusted with the implementation of the Copernicus Land Monitoring Service, which is one of the 6 Copernicus services. And Urban Atlas is part of the extensive portfolio that we offer within CLMS. We have contracted out the production to a consortium of European companies with the remote sensing expertise. And today we are going to cover the data offer, how it is produced, what to expect from the data sets, how to access the products, and of course, trying to inspire you to use the data. And of course, we also want to hear your feedback about it. Next. Some housekeeping first. The webinar is being recorded and it will be made available afterwards on the dedicated YouTube channel. Your cameras and microphones are switched off by default, and we are going to use Slido as in all CLMS webinars. We use it to collect your answers to a small number of questions we have prepared, and you can also use it to post your questions, and those will be answered at the end. So feel free to scan the QR code at the bottom right of this slide already now. You can also enter the numbers manually, and we will let you know when it's time to reply throughout the webinar. You should know as well that when asking questions through Slido, you can also vote if you find questions from someone else important. Then we're going to use that information at the end of the session to select the questions that we will answer verbally, also depending on the time that we have available. And all remaining questions will be answered and published in written format after the event, together with the recording and the presentation. Next, please. This is what we planned for you today. I will provide some background and a bit of history. I always think it's interesting to have a bit of history behind the data that we provide. Then we're going to take a look at what is new in Urban Atlas 21, and we will show you some of the novelties regarding the green urban areas classification, the improved change detection methods, and of course some details of the building block height product. After that, we will give you some information on where to access the data, because we are now moving to storing data also in the Copernicus data space ecosystem, as in other places. We are still in the transition phase with some uncertainties, but we are getting there. We will show you after a real-world application of Urban Atlas, together with other data sets, showcasing the implementation of the 330-300 rule, together with the geospatial tool for urban planning that applies that rule. And after we reach the Q&A session, where we will do our best to answer your questions. Finally, I will quickly summarize with an outlook for upcoming releases and where to find more information. Next, please. Why do we need to act? Why do we need data in cities, and why do we need to act in cities? As in the words spelled out in the EU agenda for cities that was recently published, we need data because 70% of Europeans live in cities and other urban areas. 75% of EU legislation is implemented by cities and regions. Cities are hubs of competitiveness and employment, at least the big ones, and cities play a key role in climate action. And as many of us know, living in urban areas are exposed to high and compound climate risks, such as floods, drought, and urban entitlement. So this EU agenda recognizes the vital role of cities in driving growth, innovation, decarbonization, and social inclusion. But as always, effective planning and management requires data on past and current conditions in urban areas. Next, please. So the need to have data about cities was recognized back in '98 when the Joint Research Center initiated the Murbandi project that was later followed by the Molan project. The objective of this project was to monitor the developments of urban areas and identify trends at European scale. So Murbandi stands for Monitoring Urban Dynamics and Molan stands for Monitoring Land Use Changes. And the aim of these projects was to create a spatial planning tool for monitoring, for modeling, and assessing the development of urban and regional systems. And their work included the creation of land use databases in 25 cities, together with the definition of some indicators. And the results of this work were summarized in the report Towards an Urban Atlas, published in 2002 by the European Environment Agency and the Joint Research Center together. So those were the forerunners of Urban Atlas. Next, please. So finally, in 2006, after all this preparatory work, the compilation of Urban Atlas datasets started operationally under the wing of DG Regio, so Directorate General for Regional and Urban Policy, meaning to support the work of the DG in designing, monitoring, and evaluating EU urban and regional policy. So DG Regio sets and implements EU urban and regional policy, while the Urban Atlas provides the spatial evidence base with harmonized, comparable, spatial data across European cities that make those policies more targeted, more comparable, and measurable. So this was to highlight the important role of Urban Atlas in policy development and also assessment. So DG Regio was the first client and the promoter of Urban Atlas, but we are now spreading our wings to many other users. Urban Atlas is one of the most downloaded datasets of CLMS being used in many use cases. Now, as I was saying before, the first operational production was done by DG Regio for the reference year 2006, and it covered 319 functional urban areas with the land cover land use product. Now you might want to know what the functional urban area is. It's an entity, if I might call it that, that represents a city and its commuting zone, reflecting how the urban system functions economically and socially, rather than relying on administrative boundaries. So it captures the population and the labor market, and the functional urban area serves as a special reference for Urban Atlas and also for cohesion indicators and funding analysis as well. And afterwards, the 2012 production left DG Regio and moved to the European Environment Agency, this time under the wing of GMES, so the precursor of Copernicus. And when we refer to Urban Atlas suite of products, it's because we offer more than one. And those are, as you can see in the slides, the land cover land use product, as the name says, provides land cover land use information in functional urban areas. We started in 2006 covering 319 functional urban areas. So we were covering cities with more than 100,000 inhabitants. And from 2012 onwards, we moved to covering cities with more than 50,000 inhabitants. So the data is spread over 39 countries, and the data set maps 17 urban classes with the minimum mapping unit of 1/4 of an hectare and 9 rural classes with the minimum mapping unit of 1 hectare. It's available as vector data. So since 2006, as you can see from the dates in the slides, from 6, 12, 18, 21, we have been covering a different number of functional urban areas because they also change due to changes in population density, changes in administrative boundaries, and changes in commuting patterns. So the delineation is responsibility of the countries together with Eurostat, so we don't have a say in that we have to apply the boundaries. And this is one of the biggest challenges of the product. Building a time series with constantly changing areas is quite a challenge. Most functional urban areas are stable, but there are also many that that change, that disappear, others appear. There are cases of shrinkage, cases of expansion, and all kinds of renaming as well, amalgamation. There's all kinds of situations. So it's a very, very complex and difficult to manage puzzle. We also offer a street tree layer, a separate layer showing contiguous rows or patches of trees covering 500 square meters or more over the artificial surfaces, which in the nomenclature is class number 1. So all of these inside functional urban areas, also available as vector data. And we also have building height, block height, providing height information with a spatial resolution of 10 meters in core urban areas. It's a raster data set. Additionally, we are also adding to the Urban Atlas polygons population density for 2021. This is the work being done by the Joint Research Center. And we are also working on adding to Urban Atlas polygons in 2012 and 2021 information about the local climate zones. We are categorizing the polygons in 10 built-up types and 7 land-cover types that reflect different thermal behavior. So this additional information per Urban Atlas polygon, the population density and the local climate zones is underway and will be added to the data in the coming months and published. Next. These are our speakers for today. They represent the service provider in charge of production. We have with us Alice and Johan from CLMS France. They are the consortium leader. We have UL from Cotesa, Spain, and Robin from Geoville, Austria. Not showing in the slide, we also have with us Matteo Mattiusi from the agency, is a colleague of mine, and he also will join us later on. And we also have with us Pierre Sica from Acri ST, France, who kindly agreed to join us as an external expert to show us a real-world application. Next. So this is our first slide. We want to know which type of organization you're part of. So usually we give you 15 seconds to reply, and then we move on. Of course, you can also do it throughout the presentation. And now I would like to present the next speaker, Alice Lepmou from CLS.
Hello, everyone. Good afternoon. Thank you, Anna, for the presentation of the Product Urban Atlas 2021. So I'm Alice Lernoux. I'm project manager at CLS, the French company that produces Urban Atlas data since the first reference year. Next slide, please. So yeah, I'm here to introduce you what's new in Urban Atlas 2021. So if you are familiar with the past projects, you may know that we have 26 classes and 1 second classes representing the Green Urban Area, the class 141. For this new update of Urban Atlas 2021, we propose to have additional information about the characterization of green urban area, meaning that having information of the status of accessibility, private, public, or unknown. We will develop that topic later. The other new thing in the Urban Atlas this year will be the cycle of updates. We used to working on 6-year updates in the past project, and now we have a new timeline of 3 years updates. We also have a new approach on a thematic side. We usually work as a manual approach in the past project, and now we are using a new semi-automatic change detection methodology, and we also develop this point later. Also regarding the input data, we used to work only on very high resolution data sets provided by EEA, and now we combine the use of this VHR with Sentinel-2 data time series to better identify the changes. Next slide, please. So yeah, let's have a focus on additional characterization of green urban elements. So green urban elements are defined in Urban Atlas as green areas for recreational use as gardens. So we see some private accessibility here, but also we have playgrounds, zoos, parks, castle parks, and cemetery. EEA and DG Regio requested additional information about green area to make sure that we have a more distinction between public and private, because we need a better qualification of this area for many aspects, for sure ecological and recreational functions, but also to promoting accessibility and enhancing quality of life of citizens in each country. And also this new information helping derive some indicators on access of green urban areas. So the approach that we wanted to propose is to have an automatic approach for this distinction, and Robin will explain it in detail later. Next slide is about the new timeline. So as I said, we want to improve data availability, so increased update frequency from 6 years to 3 years. Because we noticed that it gives more timely information about monitoring of urban dynamics. We know that in some Western countries, we have some Eastern countries, sorry, we have still huge urban dynamics through the year, and having an information every 3 years is still better than every 6 years. We also want to increase value for policies and urban planners that might use this data. We want also to improve responsiveness to environmental pressure, because we know that the build-up construction are taking place instead of sometimes natural lands, agricultural lands, and we have this environmental pressure on this specific landscape. So with a more timely update of Urban Atlas, we are able to see these changes quite quickly. And also we, of course, want to have a better alignment with other Copernicus projects, such as high resolution layer, for example. On the next slide, I will present you the technical enhancements that we propose for this new Urban Atlas 2021. So as I said, the past reference year were done by visual manual interpretation. So we had lots of large teams and armies of teams of photo interpreters that spotted the change between two dates. And also make a lot of creation of new cities, because as Anna explained, the number of cities grow very fast between these old reference year. Now that we have not so many work that need to be done on new FUAs, the focus is on detecting the change more efficiently. So we are going to with a semi-automatic process. So we have this first stage of having this change methodology detection methodology with AI algorithm that qualify the changes and that may occur in the difference of the two images. But we still have many manual enhancements to provide just after that, because we still need some interpreter that still need to reshape and refine polygons of change, and also provide the characterization of change between forests or urban use, for example. It also helps us to produce faster than before, because the manual methodology was time-consuming, and now this semi-automatic approach allowed us to produce faster than before and to be more in line with the reference year that we produce. And as I said, also, we used to work only on VHR datasets that are provided for each reference year. Now we wanted to add this use of time series of Sentinel-2 data to better identify, for example, seasonal changing in cities, and also update the qualification of the change. On the next slide, to summarize, so we still have this collection of projects. So we will have Urban Atlas land cover land use change detection between 28 and 21. We will also revise the status layer 28, and we'll have the status layer of 2021, so covering 719 cities, and with 28 classes. So we have these green urban areas classes that are new, and they are included in this land cover land use project. And we also have the building block height, the street tree layer, and all these projects will be also updated for 2024 quite quickly. The project specification remain the same as before. We also produce maps in PDF for each cities, as you can see on the right, providing the exact nomenclature and the colorimetry of the project. Next slide, please. Yeah, I think that's it for me. So we have this slide, second question, and we're asking, what is your primary interest in Urban Atlas data? So are you working with Urban Atlas data for urban planning, environmental analysis, climate adaptation, or more likely research or policy development? Thank you for your attention. I will leave the floor to Robin for the green urban characterization.
Hello, thank you, Alice. I'm Robin. I work as a project manager since 1.5 years now at GeoVille. We are a company based in Austria, and I'm involved in other CLMS projects on a support level. For Urban Atlas, we contributed to the change detection on the Sentinel-2 basis. And additionally, we had the task to enhance the green urban area class. Next slide, please. Yeah, and one slide. Yeah, thank you. So at first, why does access to green urban areas even matter? Urban green spaces are essential for daily life in our cities. But the problem here is that not all green spaces which appear on a map are actually accessible to the people. I will show you how the contribution of GeoVille helps the Urban Atlas better reflect the reality. Because green urban areas are not just parks, but it's also a place where communities thrive and live, where kids play, and where people cool down during hot summers. So Urban Atlas now helps answer if it's possible to use the green spaces and not just where they are located. Next slide, please. From a satellite view, all the green looks the same. From a citizen's view, clearly it's not the case. So the goal was to implement a new subclass to distinguish in the digital data set between public, private, and unknown access. And also to enhance the existing data set using additional data sources like OpenStreetMaps and TomTom. Talking a little bit about the methodology, we have the three labels, the public, private, and unknown access label. The public label is applied if public OpenStreetMaps roads, streets, or paths without restricted access, or TomTom roads or point of interests intersect the polygon. The private label is classified if more than 40% of the polygon is tagged as private, and this private class always overrides the public class. And then we have the unknown class or unknown label. This has all the remaining polygons in it, and it's to force not putting a label of either private or public on the polygon. The problematic here would be that OpenStreetMaps data, like input quality, sometimes the access is not given, or the city is just not well mapped. To sum it up, we have applied a multi-source validation, and it allows us to have a local calibration where it's required. Next slide, please. Public green spaces or public green urban areas are those that citizens can freely enter and use. These are the areas where they are most relevant for daily recreation, for health, and for social life. On the right side here in the slides, you can see the example of Hamburg, which shows a park called Planten und Blumen, which is closing during summer around 22 and in winter during 20. It's still defined as a public park in OpenStreetMaps and also in the TomTom data, even though it's closed during nights. On the next slide, you can see private and unknown labeled green urban areas. For example, backyards, fenced residential areas, airports, administrative or military land. On the picture, for example, you can see a fenced green urban area, but they provide light shows for the people, but it's still not possible to enter. So fortunately, not many green areas in Europe are private, which is nice. Some of them look accessible, but it's still unclear in reality. So mapping those differences would avoid overestimating the green space availability. The unknown access class is quite necessary for the data set when the data coverage is insufficient, and the unknown access is intentionally kept or retained to avoid the forced or unreliable attribution here. One click further. Yeah, you have the table which shows an analysis of some functional urban areas for the 2021 production, divided into the three subclasses. We have the private, public, and unknown subclass, and yeah, you see that there's not too many private green urban areas, and the unknown class is mostly below 10% in total. Yeah, next slide, please. Then we have the case study of Copenhagen. Copenhagen at first sight looks very green and accessible, with less than 5% of its green space is private. And the second site, it's also very green. It's mostly publicly available parks and green spaces. Sometimes due to the minimum mapping unit, some smaller green spaces are not included. And Copenhagen shows that treating urban green spaces as shared public infrastructure has a big effect, and it also demonstrates how consistent planning choices over the last decades translate into clear, accessible green urban areas. The next slide, please. Making the link from Copenhagen maybe to the policy. The question is, are green investments reaching all neighborhoods? With the new information from the data sets, cities can see where public green space is lacking, where inequalities exist, and also where investments into green spaces are mostly needed and relevant. The data supports, for example, the SDG 11.7 with improved monitoring of access to green public spaces, and it also identifies gaps in access to planned interventions. Then it also supports the Green Deal and their nature-based urban solutions, or the biodiversity strategy, which informs about urban restoration and planning. So the added value would be that outputs are going beyond mapping. They provide actionable insights for city planners and policymakers. It helps also neighborhoods to find their closest accessible green urban area. So another way to say it, Urban Atlas means from data to global goals. Next slide, please. Coming to the point, if a polygon has two attributes, so having a mixed accessibility, this is either due to the minimum mapping unit, it merges the polygons, but this is also when there's a big park and it's classified as one polygon, it also merges it into one polygon and not separates it. On the right side, you can see an example, the Schlosspark Belvedere in Vienna, with a small, or not small, but not 40% of the polygon classified as private, but the rest of it is a public park. The point is here that the model does not allow internal subdivision by the accessibility, which results in bigger public section forces the entire polygon into a single interpretation. And coming to the last slide, talking about the next steps, they would be identifying and integrating additional data sources to reduce unknown class step by step. Maybe worth to mention, we had a collaboration with one company, but the communication suddenly completely stopped, even though we were more than halfway through it, through the production, and the data had the impact that we were able to reduce our unknown class by more than 40%. So this shows the importance of having additional data sources. And talking about the key takeaway, by adding accessibility, Urban Atlas moved from mapping green spaces to understanding who has the actual access to make urban surrounding more livable and fair for everybody. Yeah. And then this is the end of my part. Now it's Jon from CLS presenting. Thank you.
Hello, everyone, and thank you, Robin, for your presentation. I am Jon Caumont, project officer at CLS, and I'm in charge of the production chain for the Urban Atlas use land cover products. I will now explain how we detect changes and how we produce the change layer. So compared to the previous Urban Atlas cycles, our workflow includes now more automation than before. We combine now two complementary data sources, VHR imagery, so very high resolution images, to detect small, precise changes and draw accurate boundaries. So it's very useful in the urban context. But also Sentinel-2 imagery, using time series to capture consistent temporal signals. It gives information not accessible on single date VHR comparison. Then combining results of these two analyses allows us to extract a layer of change candidates. By manual review, manual review remains essential, because not every change detected thanks to images becomes a real change in the land use land cover product in the end. For example, a new building inside an existing industrial commercial polygon is not considered always as a land cover change, because the area was already coded as industrial in the previous product. In the Urban Atlas, in fact, when we talk about industrial area, we consider the building, but also the associated areas, so parkings, storage areas, and so on. Additionally, we need to precise some characterization at level 3 on nomenclature, because images gives information about land cover, not on land use. We also have to adjust some geometries to remain consistent with the previous vintage and to respect the product specifications. We have, for example, some unauthorized changes and minimum mapping units that differ between the change layer and status layers, for example. Also manual and visual analysis are also still essential regarding quality control, validation, deliverable preparations, and so on. Next slide, please. So regarding the change detection with VHR provided by ESA, so the European Space Agency, we use an unsupervised method. That means that the process needs no training data. This method is the PCA, or Principal Component Analysis. It is a statistical method that helps us to compare two optical images by extracting only the most important information from them. It transforms the original image bands into a smaller set of principal components that highlight the strongest variations. For each pair of images, for example, 2018 versus 2021, PCA extracts the main patterns and highlights where the signal has significantly changed. So generated change heat map is visible here in the example on the bottom. On the blue means stable area on the right. On the image on the right, the blue color means that the area is stable. And as the colors shift towards red and brown, the probability of change increases. This approach is good at finding small detailed changes thanks to the highlight spatial resolution. Next slide, please. The analysis on the Sentinel-2 combines supervised and unsupervised approaches. With Sentinel-2, we benefit from many images over time on the same area, which enables time series analysis, which is a synthesis of several images on an area over a given period of time. The first step is to extract NDVI, normalized difference vegetation index from each image. NDVI tells us how active and healthy the vegetation is at every date. Once we have the NDVI time series for both years, we compare them using RMSD, root mean squared deviation. RMSD gives us a single value that summarizes how different the 2 yearly NDVI profiles are. The higher the RMSD, the more likely it is that a real change has occurred between the 2 years. Next slide, please. Time series analysis with RMSD can be tricky in agricultural areas. Because we have some difficulties with the crop rotations. So, for example, we can have wheat 1 year and sunflower the next year. That can change the seasonal signal and affect the outputs. We also have some confusions between bare soils. For example, harvested agricultural parcels with construction sites or dump sites, because of their bare soil aspect. So our solution is to combine a time series indicator with land cover classification. And for that, we use Corin land cover plus backbone, which is a 10-meter land cover product updated every 3 years. We compare year 2 and year 1 classes to derive a change detection, that what changed into what. Then we combine the Sentinel-2 time series change and the CLC plus change through a logic gate, keeping only consistent signals. So you have an example on the right, area where building appear between 2018 and 2021 are clearly highlighted in the heat map view. So next slide, please. Here is how we go from raw detections to deliverables. We harmonize and merge the VHR and Sentinel-2 heat maps. We create a binary change candidates and filter artifacts, apply MMU thresholds according to product specifications, and so on and so on. And in the end, we produce a change candidates map, which is called here change map 2018-2021. Then our partner Gisbox performs a visual manual validation. They confirm or reject each candidate, improve labels, refine geometries to align with the previous product, and revise the year 1 product. So here, for example, 2018. when necessary, they revise when necessary to keep the database consistent and aligned with project specifications. So the final outputs delivered to the EEA are the revised Land Use Land Cover 2018 product, the new 2021 product, and the change layer product. Not shown here, but delivered as a separate product. So next slide, please. Yes, here on the left, you see a VHR image and the product for 2018 reference here. We can see a main road and very early signs of works. And on the middle, we have the VHR image 2021 and the change project. So you can see large construction area clearly visible. The red polygons are the validated change areas that carries attributes for both years 2018, 2021. Not labeled here, but the information is on the polygons. And on the right, for illustrations only, a 2024 Google Earth view confirms that the transition to residential area. So we will go into residential attributes on the next 2024 land use land cover products. Next slide, please. One last example. On the middle for 2021, we can see a new construction emerging over water. And you can see that on the Google Earth view on the right for 2024, a zoomed view that shows a newly created green space, illustrating how the site continues to evolve beyond 2021. So that's all for me. Thank you for your attention. And I will now hand over to Yoel, who will present the 2021 building block height product. Thank you.
Thank you, Joan. Hi, everyone. I'm Joel Dewell. I'm from Cotesa, and we are responsible for the building block height product. Next slide, please. So our building block height has been producing since 2012, and the second iteration is for 2021. And the next will be in 3 years for 2024. So our product is based on LiDAR and satellite information, plus building footprints that we create from our internal algorithms. So merging all of this information, we generate a height model for only the building parts of the DSM that we produce. We cover, as our colleagues have said before, all the EA38 plus UK cities for 2021 at a pixel resolution of 10 meters. Our product is based on more precise information. Later, I will be giving you a QR code regarding this resolution questions or needs you may have. So yeah, for now it's 10 meter resolution with a minimum height cover of 3 meters. All the cities we produce, we consider that are pretty interesting to be considered into different studies and use cases that we have prepared for the next slides. So next slide, please. A way of combining our product of building block height could be interesting to merge it with building and density increase, also data that we can get from our building block height, measuring the changes from 2012 to 2021, and the population density that we get from Eurostat. So in this case study, you can see in the first picture changes in height variation from 2012 to 2021. And in the bottom image, you have in the left part the building density increase being from 0 to negative and from 0 to positive, and the population density also with the 0 in the middle. In this case, it is clear that we can see that it's a correlation between an increase of the density of the buildings and the population on and the population in general of the city correlated with the southwestern part of the first image, that you can see that the height variation has increased in these 9 years, and in the northwestern part that also has an increase in height variation correlated with an increase in the building density and the population. So this product unlocks new insights into urban planning and gives us more insight on what could be happening when the cities are developing. Next slide, please. So regarding, well, in that regard, we have been seeing a shift from 2D measuring to 3D density measuring in urban planning. The building height product will help on defining these new ways of understanding the cities, and the applications are pretty various, varying from urban morphology to different environmental and climate impacts that I will share with you in a couple of slides. The methodological trend shows how 3D mapping now is helping to define more ways of understanding the cities. And here are some studies that have been using 3D mapping to generate these new studies. Next slide, please. These are some examples as I finish with this use case, that sometimes there's a correlation between building heights and building density and population density, such as in Toulouse, that we can see that there's an increase in population density, but a decrease in the quantity of buildings. But as you can see, there's an increase in heights. So we can see that these parts that correspond to a low density of buildings, the buildings that are there, are higher and contain more people that they used to. But we have another cases, such as burnout, that there's not a clear correlation between this data, and there's no clear view that we can extract from that. But these are quite a few examples of what you can do with this data. So we are pretty excited about how it's going to end up in the future with these kind of products. Next slide, please. This is a use case that it's been produced by Latitudo Fori, an Italian company that did a heat wave risk modeling using the building block height and land use cover and another auxiliary info from satellite and demographic vulnerability indicators. So these are cases that are already being used our layer to produce this kind of information. So for us, it's pretty important to acknowledge for the people that these kind of data sets are so massive and give so much information that are pretty useful for different ways of understanding new urban planning. And for the last slide, if there's any improvements that you want to see, any addition, please feel free to fill this questionnaire. As said, spatial resolution can be an upgrade, and there's a lot of new fields to be developing our product. So it's all up to you now. And now I'm heading to Mateo, that will be presenting the next part of this webinar. Thank you so much, everyone.
Thank you, Joel. Hello, everybody. Good afternoon. My name is Matteo Mattiuzzi. I'm a colleague of Anna, so I'm working at the European Environment Agency, and there I'm part of the Copernicus Land Monitoring Service team. I will give you a short introduction how to access and to work with our data. Next slide, please. So before we are getting into the presentation itself, you need to know that CLMS is in the process of cloudifying its portfolio. Why are we doing this, and what does it entail to you, the use of the products? So since a few years, we have started to implement or to process large-scale products producing terabytes of data and 10,000, 100,000 and more files. So we cannot just rely on making the data downloadable. So which means that we had to bring our data to a hardware infrastructure at scale, so processing resources and storage resources at scale, so that users can avoid the download and can work directly on scalable infrastructure. This means also that we are have been reprocessing some of our products. So basically, vector files are have changed the format from the traditional JS formats like GeoPackage or file geodatabase formats, and we are now in a cloud-friendly format, which is a flat GeoBuf. Then we have the data catalog, so our data can be accessed and accessed through data catalogs and interfaced through APIs, because nobody can work with 100,000 or more files by manual interaction. So we need our data require also to have handling tools. What does it entail to you? In principle, if you are used to download the data and work on your premises, nothing changes. You can still do that. You can simply download and work the data and work with the data. But what comes on top is that you can work on cloud premises and allow you to make large-scale processes. We have moved our data to the CDSE, so the Copernicus Data Space Ecosystem, which is a large infrastructure, which is also where Sentinel data is stored. And this is where our data is physically located. If you would like to interface our data, you still have the three options. So the Land Portal, which is our legacy interface, the Vekeo platform, but also the CDSE. So you can still choose all three options. Next slide, please. So, and now is the, let's say, the farm to fork. So what is the process of our data until it reaches your table, where you then process or do something with the products. The first thing, obviously, the data is produced, and then it goes through a thorough quality assurance that makes sure that technically and thematically the products are up to the expectations. Then once that is okay, the data is published to the CDSE, and from there it is propagated to Vekeo and the Land Portal. What you see here at the bottom is the CDSE search interface, which is working, which is now the way I would recommend you to download and access the data. And you can search by keywords and or by hovering on the map. You can search and download the FUAs or the urban atlas areas that you would like to have. And then on the right, this is a mock-up. As I said, we are in the process of this cloudification. This is where the visualization is, where you can browse, click you through into the Urban Atlas products, and you can then visualize as you want the products in the map. Next slide, please. So why we have chosen to keep our data or publish our data through these three interfaces? We think that they are all very valid options and all having some nuances and differences. Effectively, we want to reach as many users as possible. So we want to reach CDSE users, Vekeo users, or the generic users on the Land Portal. The CDSE and Vekeo are similar in the matter of principles. They are infrastructure at scale with the possibility to interact with the data through APIs. They both offer instant and on-demand access to massive data volume. CDSE more for the Sentinel data. This is where the Sentinel data is stored, and Vekeo is where all the Copernicus services are storing their products. Then both offer OGC services, OpenAO, Jupyter, Lab, and R and Python kernels to do on cloud processing. Both offer the Stack catalog and the OData catalog, and Vekeo, as the difference is managed or co-managed by the Copernicus services, so you expect from it a bit more or better functionalities when you want, for instance, to combine Urban Atlas with Copernicus Marine, atmosphere, or climate change data, for instance. And then there is the Copernicus Connect, a QGIS plugin where you can easily search, visualize, and download data to your local GIS. The Land portal is where you find the description, information, and news about our products, and it's the legacy data access. It's simple to download or to select and download data, but it's not suitable for download at scale. Next, please. This is the status as of today. You see here the 4 Urban Atlas products, so Urban Atlas Status, Urban Atlas Change, Urban Atlas Street Relayer, and the building block height. You see in the reference here the 2018-21, which is the publication we are talking today at this workshop. And then we have the files which are before 2018. And this is the pattern here. On the CDSE for the current products, it's ongoing process, so you can expect, or you can see now already, you can access the data on the CDSE, but not all the services have been enabled. So there's no OpenAO enabled yet, or no visualization service yet enabled. We are aiming to publish all our products on all 3 interfaces equally. So once the products are published on the CDSE, they will be also published on WCAO and on the Land portal. For the products before 2018, for instance, we will progress with the publication soon after we have done the current job, but you can find them already on WCAO and Land portal in the full services. There's somebody doing something with the mouse, maybe. Yeah, thank you. So this means that for now you need to bear with us, be a bit patient. If you want, for instance, to access the entire time series back to 2006, then by now you have to go through 2. You don't find that in one spot, but expect this to happen soon. The same goes for the Urban Atlas Change in the street relayer, and the building block height will come. We will be working immediately after the other 3 products. We will do the same progress, but it's a little bit delayed as compared to those. By mistake, I left 2 cells blank. So the building height on the WCAO and Land portal will also, for the 2021, will also be done. So there should be a coming soon. Thank you. And then I go to this, I think the last slide for today, which is what experience do you have with Urban Atlas or AO products in general? And then we will, in a moment, we will hear an interesting use case which will be presented by Dr. Pierre Sicard. Thank you.
Okay, so thank you so much. So I can share my screen. Okay, so can you see my screen? Okay, so today I will present you a geospatial tool for urban planning, namely the rule 330-300. So air pollution, urban island, and biodiversity loss are major problems in cities, and the most important and harmful air pollutants for human health, ecosystem, and biodiversity are tropospheric ozone, fine particles, and NO2. In 2022, almost 500,000 air pollution-related deaths and more than 60,000 heat-related deaths were reported in European Union, with more than 70% of the population living in cities. By 2050, almost 80% of the population in Europe will live in urban areas, leading to more than 7 million of deaths. As you know, urban trees can provide many social and environmental benefits, like air pollution reduction, urban heat island mitigation, but also biodiversity conservation, and also recreational and aesthetic benefits, all of them leading to citizen well-being, and also by preventing, for instance, mortalities, but also hospital admission for cardiovascular and respiratory disease mainly. This is why efforts for optimizing urban greenness are needed, and we have some directives in Europe, so the European Biodiversity Strategy by 2030 and the recent Nature Restoration Law from June 2024, asking municipalities with more than 20,000 inhabitants to develop and to provide ambitious urban greening plans. However, urban planners and decision makers lack the tools to find suitable areas for greening, for instance, which species you have to plant, but also where you have to plant. This is why the rule 330-300 has been suggested for creating healthy, greener, and equitable cities. So everyone must see at least 3 trees from the home, school, workplace, because the view of greenery from home is associated with better mental health, but also psychological restoration and fever medication. Living in a neighborhood with more than 30% of canopy cover, we are associated with reduced local air temperature, mitigated urban heat island, and prevented premature death, in particular for cardiovascular disease. And living within 300 meters around home. So we have established an approach to estimate and to detect the compliance with the rule 330-300. For the component 3, so we need the building data, but also individual tree data. For component 30 and for component 302. So at the end, we are able to know if each building is compliant or not with 1 component, 2 components, or the 3 components. For the component 3, so we need all types of buildings, so house, hospital, factories, and for that we can use a QGIS, OpenStreetMap, Python package, and for each building we have to detect individual trees taller than 3 meters. For that, we create a buffer of 25 meters around each building, and we define if we have trees inside this buffer and how many. So we can use the tree layer, showing continuous rows of patches of trees covering 500 square meters or more. But also to complement, we can use very high resolution satellite imagery like World View or Pleiad with a spatial resolution of 30 or 50 centimeters of resolution in order to detect individual trees, private and public trees, taller than 3 tall meters. So very important, so we have to select satellite imagery with a very low percentage of cloud cover. So first step, if we use the very high satellite imagery, we have to pre-processing to apply the pan-sharpening approach. So pan-sharpening approach is to merge high resolution panchromatic and lower resolution multispectral imagery in order to obtain a higher pixel resolution. For the individual tree detection, so we can use the mask stepwise masking system using the NDVI. In this case, in Aix-en-Provence, we fix the NDVI, the threshold between non-vegetated and vegetated areas to 0.40. The watershed algorithm can be used for the segmentation of the tree canopy. For the tree 8, so we can use the tree stereo imagery. So in order to define and to estimate the tree 8, the difference between the digital terrain model and the digital surface model in order to estimate the canopy height model. For the component 30, so we can use the Copernicus Urban Atlas land use land cover, or also the previous very high resolution satellite imagery like Pleiad. For each building, we create a neighborhood using a 500 meter buffer around each building, and we calculate the tree canopy cover for each neighborhood. For that, we can use GeoPanda and QGIS. Otherwise, from the very high resolution satellite imagery, we can calculate the tree canopy cover with the same systems. For the last component, 300, so we can use the QGIS, GeoPanda, OpenStreetMap, and the Copernicus Urban Atlas land use land cover with different category of green urban area. So for each, we have to define a polygon for a very high quality green space with some characteristic, public, free access, but also the green space over half hectares. We have to identify entrance of each green space and to calculate the distance between each buildings and the nearest green space by following the pedestrian roads. So I can show some example in Aix-en-Provence, in southeast of France, Florence in Tuscany region in Italy. So in Aix-en-Provence, 68% of buildings are compliant with component 3 and 38% of buildings are compliant with component 3 in Florence. 94% of buildings are compliant with component 30 in Aix-en-Provence, while only 10% of buildings are compliant with component 30 in Florence. 27% compliant with component 300, and 41% of buildings are compliant with component 30 in Florence. At the end, we can combine all information, and in the case of Aix-en-Provence, 4% of buildings are not compliant with any component. 22% of buildings are compliant with one component, 56% with 2 components, and only 18% of buildings in Aix-en-Provence are compliant with the rule 330-300. In the case of Florence, only 4% of buildings are compliant with the full rule. So at the end, we can obtain for each building all information if the building is compliant, the number of trees visible from the home, the canopy cover within the neighborhood, and also the distance between the building and the nearest green area. In the case of Valencia in Spain, so 71% of buildings met the component 3, 44% of buildings are compliant with the component 300, and only 0.03% of buildings are compliant with the component 30. At the end, we have only almost 20% of buildings met no components, and almost 0% compliant with all components. This is very important. For the component 300, the characteristic free access and public access, we compare both. So if you consider the free access and the public green space, we have 44% of buildings compliant with this rule. But if you remove this characteristic, free access and public, if you consider all urban green space, you have almost 90% of buildings buildings compliant with this component in Valencia. So in conclusion, so for the component 3, so you can use OpenStreetMap data, but also individual map using very high resolution imagery like Pleiad or WorldView, because we have some limitation for the street tree layer, so with missing a few missing cities, and also the definition with a group of trees more than 500 square meter. For the component 30, so we can use the land use, land cover data, OpenStreetMap, and also the very high resolution imagery. And for the component 300, also in addition to transportation network and GeoPanda. So Urban Atlas can be used as basis information for the calculation in support with OpenStreetMap and very high resolution imagery. Very important, so Urban Atlas can help urban planner in target tree planting efforts in specific neighborhoods in order to identify green desert within cities, so to prioritize where the quarter where you have to plant. So finally, so the very high resolution Pleiad or WorldView satellite imagery can be used with OpenStreetMap and Python package, mainly for detecting the entrance of each public green space and also for accurate green space mapping, geospatial mapping and satellite-based approaches to assess the rule compliance are very important. First, in identifying area for greening, mainly in densely populated cities, but also in helping cities to develop resilient and climate-neutral urban green plans. To conclude, living in a neighborhood with more than 30% of canopy cover is significantly associated with lower premature death. Thank you so much.
Thank you. We have we are in very good time. We have reached the end of our presentations, and we are now in the Q&A session of this webinar. So we have received some questions, and I invite you to still post your questions in the Q&A and Slido. Of course, whatever we can't answer now, we will answer in written format when we post the information about the webinar, like presentation, recording, and the answers as well. Everything will be made available. I will start with some of the questions according to popularity. So the first one, it's about when will Urban Atlas 2021 be available? In case it is already published, where can we find it? Maybe Matteo, you can just again, please give a little bit of a summary.
Yes, of course. So at the it will be published on CDSC, Vekeo, and the Land Portal. In this, as of today, you can access it on the CDSC. And I assume that you will share the PowerPoint or the slides with users where they can see the URLs to access the data. So as of today, on the CDSC, in the search interface or via the S3 bucket directly, so on the storage.
Yes, thank you, Matteo. I continue. There's a second question about is a green roof of a building considered by CLMS to be a green space? I say no, but maybe I can ask Johan to reply.
Yeah. Oh, I can give it. I can give an answer. Yeah, we consider a building as it is a building, we consider it as a building. So for the use of the building itself, so it will probably be coded as a building. And to be honest, we don't. I don't remember having this case during the production time. But yeah, and because we also have a MMU that is not linked to the building itself, but we're working as a building block and not as building individually.
Yeah, thank you. Another question is, how are green urban areas that might be behind the pay barrier rather than a physical barrier? For instance, botanic gardens or zoos classed, are they private? So one of you, either Robin or Alice,
Yeah.
please.
I will go. Thank you for the question. In general, green urban areas are in the current production not classified as private just because they have an entrance fee. I don't know if a green space such as a botanic garden or a zoo is formally open to the public, even under controlled access or with a paid entry, it is generally treated as publicly accessible. A fee maybe is more handled as a management or operational condition, not a restriction of public access. And maybe if there's a pay barrier for green space, this means that the place is designed for public use rather than private use, I would say.
Yeah, thank you, Robin. I continue. Can we receive the links mentioned in the slides? Yes, you will receive all the slides, and the links are active in the slides, so everything will be available. Another one, is there any plans to lower the current 50K population threshold in order to include more cities and move toward more area-wide coverage with Urban Atlas? Not currently, because we are now starting the 24 production and we are still using the same threshold. Of course, we are aware, and we have many user requirements telling us that there's a need to extend to other urban areas. So this is something we will consider looking ahead at the future of Copernicus 3.0 aligned with the next MFF for 2834. So we have all that in our mind. We are considering other updates also of the data sets. So this is in our mind. It's not forgotten, but it's not currently for the 2024 production. Another question, is it possible to divide the three classes in more categories like parks and gardens? So this is relating to the green urban areas. Robin.
Yeah. I mean, Urban Atlas has the class 14100 for the green urban areas, which is not meant to have further classification of vegetation or different usages. Yeah, there are other CLMS products, like, for example, the coastal and riparian zones or the Natura 2000 with a finer distinction between the classes. There are also national data sets where you can look up those kind of informations, but not an Urban Atlas dataset.
No, indeed. There's many possibilities to distinguish mixed classes, and in this case, as was suggested, but we have to find out where we should stop. As an example, I can say that we are also looking into distinguish other classes, like 121, which is called industrial, commercial, public, military, and private units. It's a mixed class. We are trying also to use other input data to help us distinguish. So we are looking into many, several possibilities of improving the data for the future. I continue. This is more like a comment. Not sure how to formulate as a question. It says OSM is on voluntary basis, so it's not possible to have reference data for every area. So yeah, it's a voluntary basis, and we know that all over Europe the quality of the data differs, and that's why we are also trying to have other companies that offer mobility data, and we are trying to engage with them we had a very good exchange, but in the end, it didn't turn out with Strava data because it's also very interesting for us. It would give very important information, and we are looking into other providers as well. Also, someone asked that how do you distinguish between public and private green areas? Because the person missed the beginning. So maybe Robin, very quickly, we use other input data to help us distinguish, like OSM or Strava.
Yeah, we're also using TomTom data.
And TomTom.
And yeah, exactly. And we're making an intersection between those two data sets, more or less. And then we have the public label, and then we have the private label, and the private label always overrides the public label or the public class in case a polygon has more than 40% of private access. And then we have the unknown class, which is more a class to not force a polygon into either private or public. To sum it up quickly, maybe this helps.
Thank you. One more question about the 330-300. Do we use the residential buildings only? So Pierre, please.
Hi. So sorry, what is the question?
Yes.
If I use.
In the 330-300, do we use the residential buildings only? That's how
No. Also, factories, industrial buildings, but also schools, high school education, all buildings, all type of buildings.
Yes, thank you. And one last question that I can see here, which is the relationship between these presentations and the nature restoration law that is at national level? Well, the nature restoration law looks at two CLMS data sets that are not urban atlas. So it looks at the high resolution layer treacle density and this for one of the indicators, and looks at the CLC backbone for the second indicator. So urban atlas was not considered because of the reason mentioned before. We don't cover all urban areas. So we cover most cities, but not small cities. So, but still we have, countries are entitled to use other data, and they can also still be willing to use urban atlas data if it exists for their city, for their urban areas. So it's not obligatory to use only the HRL treacle density and backbone. Countries can also decide to use other data sets, and this is one that can be used if it found appropriate. Thank you for the questions. I think we can move on now for summary and conclusions. Yes, maybe one slide more. This is just a summary as a reminder of what we offer. We map and cover land use change across Europe in functional urban areas. We include the building block height and the street tree layer layers, and we hope to facilitate an extensive time series in diverse applications because we have been mapping urban areas since 2006. As we discussed today, upcoming or right now becoming available is the Urban Atlas 2021, and the production for 2024 already started, even though there are still some issues to solve with the completeness of the VHR 2024 coverage. In addition, we also plan to validate the 21 and the 24 productions in an independent exercise. And we have already received the validation of the building block height 21, and the land cover land use is on the way. We received them, we are reading them, and they are almost ready to be published soon as well, together with the data. And it will be followed by the street tree layer. And of course, we will do the same for the 2024 products. Next slide. If you scan the QR code on the right, you can find all the information about Urban Atlas in the CLMS website and in the and one question popping up. I will address it a bit later. In the documentation section, you will find the product user manual and the algorithm theoretical basis documents. So they are available as PDFs and also through the technical library in a different format. Maybe I can address one question that was asked during the presentations regarding the acknowledgement of OSM. Yes, of course, we will do that. I'm just having a look at the chat. Claudia, usefulness of the webinar. I'm not sure if we have that question. Yes, we have. And you can also tell us the usefulness of the webinar in a scale 1 to 5. So you can find it in Slido. And next slide, please. Now, if you don't want to read all the documentation, you can also choose to ask the Copernicus service called Observia. Observia simplifies intricate information for user comprehension, provides clear explanations and contextual understanding, enhances user engagement through interactive information, and tailors the complexity of content based on user questions. It was built on a European LLM, Mistral 7D, and it's harvesting knowledge from trusted sources. And of course, you can also address us with questions through the service desk. You can find the links in the slides. And last slide, please. We have reached the end of our webinar. With that, oh, there's no slide, of course not. With this, I would like to thank all of the participants for your contribution, for your questions. I also want to thank our speakers for their very nice contributions. Also the people in the background facilitating the webinar, Sean and Claudia. And I wish you all nice rest of the day, and I hope to see you soon in upcoming CLMS webinars. Thank you very much and goodbye.